Here we're asked to evaluate the definite integral of x squared over the quantity x squared minus 1 raised to the 5/2 power from 2 to 3. We can solve this problem using trigonometric substitution, and we need to notice that the form of the denominator has the same form as the square root of x squared minus a squared. Happens to also be raised to the 5th power, but it has this form where a is equal to 1. When you see an integral with an expression of this form, you should let x equal a times secant of theta. Here a is 1, so x is just secant of theta. Next, we're going to need to have an expression for dx. The derivative of secant is secant times tangent. And since this is a definite integral, we need to change the limits of integration as well. So the upper limit was x equals 3. We can find theta by doing the inverse secant of x. The inverse secant of 3 isn't like a simple number, so I'm just going to note it with a symbol theta 3 so that we don't have to keep writing inverse secant of 3. We'll have this shorter notation. When x is 2, theta is equal to the inverse secant of 2. That one does simplify down nicely to just pi over 3. That's actually because cosine of pi over 3 is 1/2, and secant is 1 over cosine. Now, we need to go and start making our substitutions. We'll start by changing the limits of integration. The upper limit changed to this angle theta 3, and the lower limit changed from 2 to pi over 3. We let x be secant of theta, so this x squared and this x squared both turned into secant squared. And dx, we calculated that as secant theta times tangent of theta times d theta. So that's where this part of the numerator is coming from. Next thing I'm going to do is try to simplify the secant squared of theta minus 1 by using a trig identity. It's going to be a trig identity that we derive from cosine squared plus sine squared equals 1. What I'm going to do is divide both sides by cosine squared. If I divide every single term by cosine squared, I end up with 1 plus tangent squared is equal to secant squared of theta. Now, this expression actually has secant squared minus 1, so what I need to do is subtract the 1 to the other side. And after I do that, I see that secant squared of theta minus 1 is just equal to tangent squared of theta. So this expression in the denominator can be replaced by a tangent squared. Now we have tangent squared of theta quantity raised to the 5/2 power in the denominator. We'll simplify that. When you have a power in parentheses and a power outside, you multiply the powers. So we're going to end up with a power of 5, tangent to the power 5 in the denominator. And clearly there's more that we can simplify. Like I've got secant squared times secant, and tangent over tangent to power 5. Turns out that the best thing to do is write it all in terms of cosines and sines. And after you cancel and simplify this expression, you end up with cosine to the power 1 of theta over sine to the power 4 of theta. Now, when I look at this expression, I need to think of ways of integrating this. And one way I could integrate this is using the method of substitution. Not trig substitution, just normal substitution. The reason I know that I can do that is because if I let u be sine of theta, the derivative of sine of theta is cosine of theta, and that appears as a factor in the numerator. So I'm going to do that. I'm going to let u be sine of theta. And we're going to need more space. So let's move this back up to the top. We're going to now let u equal sine of theta. Then we need to figure out what du is. But in this case, it's just cosine of theta times d theta. In other words, it's the entire numerator of this expression. Since we change variables, we again have to change our limits of integration. The upper limit of integration was theta equals theta 3, where theta 3 was the inverse secant of 3. And that means u is going to equal sine evaluated at theta 3. And you can either figure that out by making a right triangle such that secant of theta is equal to 3, or you can use a calculator. Either way, you end up with the square root of 8 over 3. The lower limit of integration also needs to change. Right now it's a value of theta, and it's pi over 3. When theta is pi over 3, u is going to equal sine of pi over 3, which is root 3 over 2. So now we have our new variables, our new limits. We can change our integral. It is now the integral of du over u to the power 4 with our new limits of integration. And as usual, when you have u to some power in the denominator, you're going to want to think of it as actually having a u to the negative 4 power so that you can use the power rule for integrals to integrate. So I'm going to do that. I'm going to increase the power by 1, then divide by the new power. So I end up with u to the negative 3 power divided by 3, evaluated at these limits of integration. And then you can plug in the upper limit minus what you get when you plug in the lower limit. Skipping some of the numerical details, you end up with the following: 8 over 9 times the square root of 3 minus 9 over 16 times the square root of 2. That is the final result for this integral.